let's get started. My name is Erin. I'm going to be introducing our speaker today, Alessandra Carlotta Re. She graduated in 2008 at the University of Milano Bicocca with a thesis on low-level radiation measurement at Gran Sasso National Laboratory. During her PhD, Alessandra was at the University of Milano Statale, and she joined the Borexino collaboration and started working on neutrino physics. She's still a core member of the Borexino collaboration. After her PhD, she got several fellowships from the Italian National Institute of Nuclear Physics, where she was continuing to work on neutrino physics. In 2013, she joined SOX, the short distance neutrino oscillation with Borexino, and from 2018, the JUNO collaboration. Right now, Alessandra has a permanent position at the University of Milan, where she teaches and continues her research on neutrino physics. So take it away, Alessandra. You can put questions in the chat, but we'll hold off on question time until the end. Still muted. Don't forget to unmute.
Okay, can you hear me now?
Yes, perfect.
Okay. Yeah, no, okay. So thank you, Erin, for the introduction, and good evening to everybody. I'm Alessandra, and I'm going to talk about the latest great achievements of the Borexino experiment, that are the complete spectroscopy of the PP chain solar neutrinos and the first direct measurement of the CNO solar neutrino flux. I'll start with a brief review of what solar neutrinos are and how they are described by the standard solar model. Then we will move to discover how the Borexino experiment works, how the detector works, and we will focus on how it was possible for the collaboration to actually measure the CNO neutrino flux. A first question one could think of is why we still study solar neutrinos today. Well, there are at least two physics fields that can profit from solar neutrino studies. Particle physics, where we look at the sun as a powerful neutrino source, and astrophysics, where we look at solar neutrinos as messengers of astrophysical events. As regards astrophysics, the main purposes are to test and study stellar models and to solve the so-called metallicity problem. In fact, following a reevaluation of the photospheric chemical composition of the sun, the new refined lower metallicity inputs to the standard solar model leads to results at odds with the helioseismological measurement, hence the puzzle, the metallicity puzzle. As for the particle physics field, instead, the main results could come from flavor oscillation physics, from the precise measurements of neutrino oscillation parameters, theta 1, 2, and delta m squared 2m, and as well as from hints to physics beyond the standard model. We know that our sun shines in neutrinos. This is due to the fusion reactions that occur in its core, and that can be summarized in the equation here reported with a net energy release of about 26 MeV. Neutrino interacts only through weak interaction, and at the mean energy of solar neutrinos, roughly 1 MeV, this means that we deal with a cross-section of 10 to the minus 44 square centimeter. Given their nature, we know that neutrinos are a very powerful tool to study astrophysical objects. For instance, considering the sun case, a photon will massively interact with the plasma, the solar plasma, and take about 10 to the 5 years to reach the star's surface. Instead, with neutrinos, it only takes about the famous 8 minutes to travel from their production site in the core of the sun to the surface and then to the Earth. So solar neutrinos are the most unique natural tool we have to perform a solar neutrino spectroscopy. That is the only way to get a real snapshot of the sun, and so true real-time informations. Solar neutrinos are the neutrinos emitted during the two processes that make a star to burn: the PP chain, proton-proton chain, and the CNO-cycle. In particular, for small medium stars like, let's say, having a sun-like mass, the proton-proton chain is responsible for about the 99% of the energy release of the star, while the CNO-cycle for the remaining. In the PP chain, we have 5 solar neutrinos, the so-called proton-proton PP solar neutrinos, the PEP neutrino, the HEP, the beryllium-7, and the boron-8 neutrino. As for the CNO-cycle, instead, we have 3 other solar neutrinos coming from the reaction involving nitrogen, oxygen, and fluorine. The solar neutrino fluxes are well described by the so-called standard solar model, which is a complex container where input parameters such the sun luminosity, the radius, the mass, the composition, the cross-section of the processes involved, the opacity, the metallicity, are considered all together and result in expectation about the neutrino fluxes and heliosismology. There are quite different predictions according to the different metallicity input, and talking about the solar neutrino fluxes, the metallicity scenario results in about a 9% difference in the estimation of the beryllium-7 solar neutrino flux, in about 18%, an 18% difference for what concerns the boron-8, and about the 28% difference for the CNO, nitrogen, oxygen, and fluorine neutrinos. The solar neutrino energy spectrum extends up to about 20 MeV. Here you see the spectrum of each neutrino species with its theoretical uncertainty according to one of the most up-to-date solar model, the Barcelona 16. And introducing Borexino original goal, its original goal was the measurement of the sub-MeV beryllium-7 neutrino rate alone. But actually, during the years, Borexino turned out to be a quite flexible experiment, let's say, and we were able, in the end, to scan and study basically the whole solar neutrino energy region. Due to the very small neutrino interaction rate, we have seen before that the cross-section is of the order 10 to the minus 44 square centimeter. Solar neutrino physics is rare event physics. The shielding against the cosmic rays and experiment extreme radiopurity are crucial to perform any measurement. Solar neutrinos experiment can be carried out in underground laboratories only, basically, and Borexino, in fact, was located in the OC of the Laboratori Nazionali del Gran Sasso, a place that guarantees a shielding capacity against cosmic rays of about 3,800 meter water equivalent. This yield to the muon flux to be reduced by a factor 10 to the 6 with respect to the muon flux measured on the surface. In Borexino, the detection method is elastic scattering of neutrinos on electron. So what we actually see and study is the energy carried away by the electron, not the neutrino energy directly. The detection medium is a large mass of organic liquid scintillator, which features some pros and some cons. The main advantage was for sure the large light yield. The main disadvantage was that we were not able to extract any directional information from our signal. So in Borexino, the signal is indistinguishable basically from the background, and high radiopurity is a must. To give you an idea, the expected rate of solar neutrinos from the beryllium-7 reaction in 100 ton of the scintillator in Borexino was about 50 counts per day, which roughly corresponds to an activity of 10 to the minus 9 becquerel over kilogram. And for comparison, the tap water, the water we drink, is about usually 1 becquerel per kilogram in uranium, thorium, and potassium-40. The constraint of such a high radiopurity requirement was fulfilled thanks to the Borexino detector structure, which exploited the principle of graded shielding. The more we go towards the center of the detector, the purer the detector is. Starting from the external, we have the water tank, the structure here, the dome here, that acts as a gamma and neutron shield, as well as a Cherenkov detector for the cosmic background. Then we have the stainless steel sphere, this structure here, on which the photomultipliers were installed. And then we have the non-scintillating buffer, 2 nylon vessels to further prevent contamination from the PMT's radioactivity, for instance, to get inside the core of the detector. And finally, the scintillator, the very core of the Borexino detector. The Borexino history lasted about, let's say, more than 30 years, starting from 1988, when the first talk about a large liquid scintillator detector were given, to the actual proposal in 91, to May 27 in 2007, when the DAQ was officially switched on. And then more than 14 years of data taking and impressive measurements until October 2021, when the decommissioning has officially started. Let's now see how is it possible to extract a neutrino signal from the Borexino data. Even at the Borexino very high radiopurity conditions, we still have backgrounds, of course, background events that contaminates our solar neutrino signal, and we need to apply software cats to the data in order to remove as much as possible the background. Looking at this plot, you see an example of a Borexino energy spectrum in NPMT's DT1, which is one of our energy estimator, and roughly in NPMT DT1, 400 NPMT DT1 corresponds to 1 MeV here. The same data set, so the black is the original, let's say, raw spectrum. The same data set after applying the removal of muons is reported, is reported in blue. Then we have another fundamental cut, which is the selection of a fiducial volume in red, the dataset after the selection of a fiducial volume. And finally, in green, the dataset after the subtraction of one among our main backgrounds, the carbon-11, and we will see it better later on. The algorithm we use to tag and get rid of this very dangerous background is called the threefold coincidence. Briefly, every time we have a muon crossing the active scintillator zone, there is a chance that this muon interacts with a carbon-12 atom of the scintillator and produces carbon-11 together with cosmogenic neutrons. We hence exploit the time and space correlation between muons, the neutron produced in combination with the carbon-11, and the decay of the carbon-11 itself to obtain a likelihood that a certain event is really carbon-11. To summarize, so far, which the Borexino had never been so performing, which would count on the best radiopurity thanks to of course, the natural decay of the radioisotope, but also to thanks to the several purification campaigns we made through the years. We could count on high statistics and mostly on an optimal comprehension of the details of the energy scale and the detector response function. So for the first time, it was possible to think about and to actually perform a simultaneous fit on the whole solar neutrino energy region, so completely mapping both the PP chain and the CNO-cycle. And this ambitious goal was reached in 2 steps. The first in 2018 on Nature with the measurement of all the solar neutrinos fluxes related to the proton-proton chain. And then again in 2020 with the CNO solar neutrino measurement, an analysis that was, sorry, I have a connection unstable warning, but I hope everything is fine. Can you hear me?
Yeah, but maybe turn off your camera and then it'll
Yeah,
help.
I'm sorry. I have a turn. Yeah, okay.
Yeah, no worries.
Okay, maybe now it will be better. I was saying that, okay, this analysis on Nature actually earned Borexino the cover of the issue and a nomination among the top 10 breakthrough of physics world in 2020. So in the next slides, I will focus on this work, but the general idea that I will explain for this analysis is really the same that was used also for the PP chain analysis. So let's now see how the CNO neutrino signal can be extracted from the Borexino data. In this plot, in logarithmic scale, you see the Borexino energy spectrum of the events used for the CNO analysis, collected in about 1070 days of the DRQ, in the energy range we used to fit, that is 0.3 up to 2.6 roughly, MeV, after the preliminary softer cuts that I described before, so the removing of muons, the selection of a fiducial volume, and the tagging subtracting of the carbon-11. But where are the CNO neutrinos in these pictures? Well, here you see, depicted in red, the CNO spectral shape normalized to the standard solar model high metallicity expectation. As we will see now, this signal is really submerged by residual backgrounds. The strategy we adopted was to exploit the difference in the energy distribution of the signal and backgrounds to separate one from the other. The PDFs of both these components were generated via Borexino tailored GEM4 Monte Carlo. Like I said, CNO neutrinos are just one of the contributions we do expect to have in our region of interest after the previously discussed cuts. In this plot, you can see what is expected to lie beneath the full Borexino spectrum, the CNO neutrino, of course, in red, together with the spectral shapes of the other solar neutrinos, beryllium, PEP, and boron, and those of the main backgrounds contributions, so the external backgrounds in gray, as a consequence of lead 2010 contamination. We also have the bismuth 210 in green and the polonium 210 in yellow. There is also krypton 85 in dark green here due to the radioactive follow-up of the atmospheric nuclear test in the 1960s. And the carbon-11 in purple, which, as I already discussed, is our main cosmogenic background. And actually, it's the most dangerous background if we want to measure the CNO and PEP and PEP neutrinos. Established that, anyway, we know how to get rid of the carbon-11 contamination, or at least we know how to tag carbon-11 event. The main problem we still have to face is the similarity between the CNO red, PEP blue, and bismuth 210 green spectral shapes. Similarity that is clearly visible, okay, looking at the play, at the plot here, where I report the data set and the spectral shape. And also, moreover, even the predicted neutrino rates do not help in the sense that in lieu of 4 or 5 counts in CNO, we do expect 3 counts in PEP neutrinos and about up to 15-20 counts in bismuth 210. So everything about these 3 species has to be carefully balanced. This correlation is even clearer if we look at these sensitivity studies done with thousands of Monte Carlo pseudo experiments. To reduce them, we impose a constraint over the PEP ratio. And the constraint is described in detail in our Nature paper of 2018, so the one of the PP chain complete spectroscopy. Roughly, the PP value is constrained with a 1.4% precision to a value inferred from a global fit to solar neutrino data, and imposing both the PP-PEP ratio and the solar luminosity constraint. So we remove the correlation between PEP and CNO, but still the bismuth 210 spectrum is quasi-degenerate with the CNO neutrino one. You see that the correlation is very pronounced. There is a solution. The bismuth spectrum can be constrained, the bismuth rate can be constrained by precisely and independently mapping the polonium rate. Why? Because this is possible since both the polonium and the bismuth are daughters of lead 210. And at secular equilibrium, the rate of bismuth 210 is equal to that one of polonium 210 by definition of secular equilibrium. The polonium, here you see the usual plot with the addition of the polonium 210 spectral shape in yellow, is really much easier to identify with respect to bismuth since it decays alpha, and so it's characterized by the ammono-energetic Gaussian peak. And so what we need to do is to precisely measure the polonium rate, and so to get the real and only supported term of this chain related to bismuth. So it seems that we have the solution then, but unluckily we discovered in 2015, if I remember well, that we had convective motions inside the detector due to the seasonal temperature changes inside the detector. And these motions brought inside the active volume of the detector an unknown amount of polonium 210 that was previously present on the surface of the inner nylon vessel. This contribution broke the secular equilibrium of the lead 210, and so we were not able to extract the rate for the bismuth. Before performing any analysis, we had to thermally insulate the detector to stop the convective motion. And this was achieved by creating a stable and vertical gradient to prevent these motions. Here you see 2 pictures of the Borexino detector before and after the cure. So before and after being covered with 20 centimeters of rock wool. And the temperature of the detector since then was constantly monitored by 54 sensors, and it is now stabilized. I report here the progress of the stabilization in this plot, where we have the time evolution of the polonium contamination in Borexino. The color scale is the reddish, the more reddish, the more counts, in a vertical projection of the detector from the bottom to the top. The red curve represents the average temperature in the innermost region surrounding the nylon vessel, and the change is color. Here you see the oscillation, the seasonal variation, the oscillation of the polonium cloud. The change in color is due to the natural decay of the polonium-210, but also, okay, now from a very stable and stable situation, let's say. So once we reached the stable situation, we could proceed with the measurement of the supported polonium rate. In particular, we found an innermost region of the scintillator, which was almost free of convective currents, and we could fit there in this region the polonium rate by assuming a bulk plus radial contribution. We got a minimum for the polonium rate, and so we were able to set an upper limit for the bismuth rate. The bismuth rate, this upper limit, could be extended over the full fiducial volume and not only to the region. If and only the bismuth was found with the error uniform both in the angular and radial distribution. This was the case, thanks. We were very happy about this. So this was our case, and we could finally report a bismuth 210 upper limit of 11.5 plus or minus 1.3 counts per day in 100 tons of scintillator. That said, we finally can extract the neutrino rates by fitting the experimental data with expected spectra of signals and backgrounds. We perform a multivariate fit, and we obtain the neutrino interaction rates by maximizing the bin and likelihood function, which is given by combining the contribution from the simultaneous fit of the energy spectrum, which is presented as two separate, actually, energy spectra, one depleted in C11 and one with the C11 included. And the radial distribution of the very same events belonging to these plots, so to improve the fit capability to disentangle external backgrounds from the neutrino signal. The rate of the solar neutrino signals and backgrounds were, of course, free parameters of the fit, with the two discussed exceptions, the bismuth 210 and the PEP. The complete fit of our data resulted in a measured rate for CNO solar neutrinos of 7.2 plus 3 minus 1.7 counts per day over 100 tons of liquid scintillator, yielding to a measured flux for CNO of 7 plus 3 minus 2 times 10 to the 8 neutrinos per square centimeter per second. This result is consistent with both the high metallicity and low metallicity prediction. Last year, on December, so a few months ago, we published on Physics Review Lectures an improvement of this analysis thanks to an enlarged data set plus 32% exposure. The exposure was greater with respect to the Nature paper in 2020. A better constraint of the bismuth 210 and some Monte Carlo refinements. The main results we obtained with this update was improving the detection significance of CNO. In fact, we were able to reach the 7 sigma significance. And also we actually got some other bonus, some other astrophysical implications. So here you see the results in the version, basically the new version of the previously shown plots, with a rate that now is 6.8 plus 2 minus 0.8 counts per day in 100 tons of liquid scintillator, corresponding to a measured flux of 6.6 plus 2 minus 0.9 10 to the 8 neutrino per square centimeter per second. A first astrophysical implication comes from the global analysis of the solar neutrino fluxes. So assuming the standard solar model high metallicity scenario and the Borexino results on beryllium, boron, and CNO, we were able to exclude, to disfavor, the standard solar model low metallicity scenario at a level of 3.1 sigma, about 3 sigma level, let's say. And a second astrophysical implication regards the determination of the carbon plus nitrogen core abundance in the sun. This was a first measurement of this parameter using the CNO neutrinos. And well, solar neutrino, we know that solar neutrino fluxes, both coming from PP chain or CNO-cycle, depend on the sun environmental parameters, basically on the metallicity, the opacity, the one I listed before. But this dependence is indirect. The real dependence is the core temperature. So, and in this parameter, for this parameter, the most sensitive signal is the one coming from the boron 8 neutrinos. In addition to that, to this, let's say, dependence on the temperature, the CNO solar neutrinos fluxes are also directly linked to the carbon and nitrogen content in the solar core. There is this strong dependency also on the metallicity scenario. And so this value, the value of the abundance, will vary according to the metallicity chosen, to the chosen metallicity. And there could be up to a 30% variation. We hence use a precise measurement of the boron 8 solar neutrino to constrain the temperature, the core temperature, and so to extract the carbon-nitrogen abundance in the core of the sun. So we find again an agreement with the high metallicity hypothesis and a mild tension of about 2 sigma with the low metallicity scenario. This work, this analysis, is currently completely dominated by the experimental uncertainty. So I come to my conclusion, actually. Solar neutrinos were and still are essential in proving how the sun shines and in discovering and studying the physics of neutrino oscillations. Borexino, during his life, was able to map the entire proton-proton solar fusion chain with high precision, very high precision, and it has demonstrated the existence of the CNO solar neutrinos with a current significance of 7 sigmas. The combination of the results from beryllium and boron neutrino fluxes have shown a mild preference towards the standard solar model high metallicity scenario. And the first determination of the carbon plus nitrogen core abundance based on CNO neutrino fluxes was obtained. So Borexino, as I was saying, is now in decommissioning, is a closed experiment. We are still using the tons of data we collected in 14 years of the DAQ. But in future experiments, maybe we'll be able to provide a precise measurement of the CNO neutrinos, and this measurement could give us a key knowledge of the sun metallicity and of how the massive star burns. And I thank you for your attention.